Hello and welcome to yet another video of Cornerstones of Math. In this video, we are going to prove this very famous inequality known as the arithmetic mean, geometric mean, harmonic mean inequality. Now, this inequality can be easily proved by simple algebra, but in this video, I am not going to prove it algebraically. I am going to prove it geometrically using this specific setup, which includes this parabola. Now, this is the detailed explanation for our setup, but because reading is boring, even in the educational math video, I am going to visually explain it to you. But before we get to that part, we first have to properly define what a parabola is. And instead of usual quadratic function characteristic of a parabola, let us use the geometric definition of a parabola. That is, a parabola is a collection of all points that are equidistant to a point called the focus and a line called the directrix. And this equidistant property will be crucial for our proof, which I am about to explain right now. So consider a parabola with focus F and directrix L. Draw a line which passes the focus F and intersects the parabola at 2 points P and Q. Next, let us take point M, which is the midpoint of line segment PQ. Next, we take some points on the directrix. Let P', F', M', and Q' be the foot of perpendicular of P, F, M, and Q on the directrix L respectively. Then we let the length of P' as A and the length of Q' as B. Here we want to use this figure to prove the following arithmetic mean, geometric mean, harmonic mean inequality. Okay, let's get on with it. And actually, the very first thing that I'm going to do is, without loss of generality, assume that A is less than or equal to B. If the length relation is other way around, the proof is just symmetrical. Next, let us draw additional line connecting points P and Q'. Suppose that this new line segment PQ' intersects the line segment FF' and MM' at points F' and M' respectively. Now it's time to make use of the midpoint property related to point M. This means that the foot of perpendicular M' is also the midpoint of line segment P'Q'. Here, by the midpoint theorem of triangles, length MM' is equal to B over 2 and M' is equal to A over 2. Therefore, this length MM' equals A plus B over 2, which is the arithmetic mean. Our next interest is this length FF'. Here we use the key point of the parabola that any point on the parabola is equidistant to focus F and directrix L. That is, length PF is equal to length P', which is A, and length QF is equal to length QQ', which is B. Here, the length of FF' can be obtained by adding up length FF' and F'. And these lengths can be obtained from simple similarities between triangles. First, from the similarity between triangles PQQ' and PFF', that is, this triangle and this triangle, the ratio between FF' and QQ' is equal to the ratio between PF and PQ. That is, the ratio this to this is equal to the ratio this to this. So we have FF' over B is equal to A over A plus B, which gives FF' equals AB over A plus B. Next, from the similarity between triangles P, P'Q and F double prime, F prime, Q prime, that is, this one and this one, the ratio F double prime, F prime to P, P prime is equal to F double prime, Q prime to PQ prime, which is then equal to FQ to PQ. That is, this to this equals this to this, which again equals this to this. So we have F double prime F prime to A is equal to length FQ is B and length PQ is A plus B. So we have F double prime F prime equals AB over A plus B. Here, notice that F double prime and F double prime F prime are equal. This means that the point F double prime is equidistant to focus F and directrix L, which makes F double prime the point on the parabola. This is an interesting fact, and adding these two, length F prime is given by 2AB divided by A plus B, which is the harmonic mean. So we have found the arithmetic mean and the harmonic mean, but where is the geometric mean? Well, let us now focus on this distance right here, the length of the line segment FM prime. Here, let us delete some lines that are no longer required, and let us draw some new additional lines. That is, let us connect P prime and F, and also Q prime and F. Due to the aforementioned equidistant property of parabola, we know that triangles P prime F and Q prime F are both isosceles. That is, in terms of angle consideration, if we let the measure of angle P prime F be alpha, then angle PF prime is also alpha, and if we let angle Q prime F be beta, then angle QF prime is also beta. Moreover, due to the alternate angle relation, this angle P prime F prime is also alpha, and this angle Q prime F prime is also beta. Therefore, we have 2 alpha plus 2 beta equals 180 degrees, which gives alpha plus beta equals 90 degrees. But notice that alpha plus beta is the measure of the angle P prime F Q prime. Therefore, we have the right angle right here, making triangle P prime F Q prime the right triangle. Therefore, this point M prime is the midpoint of the hypotenuse of the right triangle P prime F Q prime, and you know what that means. This means that M prime is the center of the circumcircle of the right triangle P prime F Q prime. This means that not only do we have P prime M prime equals M prime Q prime because midpoint, but these lengths are also equal to FM prime because it is the radius of the circumcircle of the right triangle P prime F Q prime. So in order to find the length of FM prime, we only need to find the length of either P prime M prime or M prime Q prime, which can be found like this. Let H be the foot of perpendicular from point P on the line Q prime. Then length PH, which is also equal to length P prime Q prime, can be obtained from the Pythagorean theorem, square root of PQ squared minus QH squared. So we have square root of length PQ is A plus B and length QH is b minus a. And if you simplify this, we simply have square root of 4ab. Therefore, 2 times square root of ab. Therefore, length fm prime, which is also equal to length p prime m prime, is just 1/2 of length p prime q prime, which is just square root of ab, which is the geometric mean. So we have the geometric mean right here. And we have already found the length corresponding to the arithmetic mean and the harmonic mean. So if we make geometric length comparison among these line segments, we can see that length m prime is greater than or equal to length fm prime, which is then again greater than or equal to length f prime. And therefore, we have the arithmetic mean, geometric mean, harmonic mean inequality. Lastly, let us check the equality condition. The equality holds when m prime is equal to fm prime, which is equal to ff prime, which is equivalent to a equals b. And that's all for today's video. Thank you all for watching. Please don't forget to hit the like and subscribe buttons if you enjoyed this video, and I will see you in another video.